Yes. Forgot to put my headset on. Sorry about that. This lecture, take me a while to sort of put this lecture together, but this lecture is going to look at multiple sliding surfaces. So in both ways, one on top of the other and one next to the other. I'm going to do a couple problems to sort of show that too. But the first one I'm going to solve symbolically. So multiple sliding surfaces. That's what we're going to look at under friction. That's what we're still looking at. Now, the first one that I want to look at today is I want to, well, I think I shifted that a little bit. Anyway, first one that I want to look at today is two things on an inclined plane that are on top of one another. So I've got two different packages here, right? And I'm going to say that the surface between this is mu sub S1, and the surface that we have down here will have a static coefficient of mu sub S2. All right? And so I'm going to call this weight 1, and I'll call this weight W sub 2. All right? So we have those on an inclined plane. Obviously, we're going to have, components of those. I'll draw this W1 a little bit longer so that I can show that we have components in the normal direction, W sub N, and, in this case, that'd be W1 sub N and W1 sub T. But we can do exactly the same thing for W2, right? So that's what we want to look at. We want to look at, and I'm going to come up later on, I'm going to actually throw some numbers in there so that you can sort of see what we're doing. But the first thing that I want to analyze is the top block, right? Block 1. That's block 1, and this is block 2. So let's analyze block 1 all by itself. Right, we'll draw a free body diagram just of block 1. Now block 1 has W sub N, right? It has a normal force. This is the normal force between 1 and 2, right? Pushing up because it's only got one force pushing down. And then it's also got W sub T. And this would be W sub T1, W sub N1. And then this is sliding down between block 1 and block 2. We don't have to worry about block 1 and block 2 at all. All we have to do is figure out that this is the frictional force, right, between block 1 and block 2. And we know what that would be. That would just be the normal force here of 1 and 2 times the coefficient of static friction between the blocks 1 and block 2. So let's just sum the forces in the x direction equal to 0 for this, and I would have F sub R 1 dash 2, right, minus W sub 1 times the sine of theta, right? Whatever theta is, and of course this angle here is theta, isn't it? All right, and of course this angle right here is theta too. So this is theta. I think I could probably draw that in right there. That is theta. There you go. So both of those two are theta. And so we know that the W sub t here for the first one is going to be W sub t1 is going to be W1 times sine theta. I don't think I have to really, point that out. And then if we sum forces in the y direction equal to 0, we just get that, in fact, I'm just going to write it out as n equals W cosine W1 cosine theta, right? Everybody sees that? I thought I had some other pens around here, but, oh wait, here it is. Yeah, I've got it. Okay, so let's just look at this then. So we've got that on top there, and we can see if we were to put this all together, put these two different equations that we have here together, because we know that f sub r12 is just going to be mu sub n, and that's going to be mu, so mu times w cosine theta has got to equal w, and this is w1 times sine theta, right? And the w1s cancel out on both sides, and what that shows us is that the inverse tangent of mu sub s 1 equals theta. So that would tell us what the angle is that this is rotated to, at which point this will slide relative to the block right underneath it. So block 1 is going to slide when the angle equals the inverse tangent of mu sub s1. Now, let's analyze the second block, the free body diagram of the second block now. Now, let's just draw the second block all by itself right here. Right, this is the second block. So if this was block number 1, this is going to be block number 2. Block number 2 has a variety of different things that are sort of, working on it. It's got the weight force. It's got Wn sub 1, so W1 is pushing down on it. W sub N2 is pushing down on it, right? Now it doesn't have anything going on here unless this is working on that. And what we'd have to see here, we'd have to actually find out, if that were sliding. So we would have to know this before we could really, solve this problem. Because if this is sliding, actually, if this is sliding on top, it's not going to really make any difference as compared to the weight force that's moving down here. It would actually, if this is sliding on the top, this would put some type of force on here. Actually, it would put a frictional force on here, whether it was kinetic or static, right? Anyway, let's do the rest of it. So I've also got my W sub t on the end, and this thing now is going to be working against, just like this one was here, F sub R2 is going to be working against the motion of this moving down on the thing. And of course, F sub R2, I'll just finish this off. This is going to be my normal. I should put normal 2 here, and this one should have been normal 1, so that we could just separate. Oh, one, I think I called it 1, 2, and this would be like 2 to the surface. I'll just put surface there. See, did I leave that out anywhere else? No. Okay. So we've got all of that set up there. Okay, so Let me put this one right on here like that. So we've got Wn sub 1. Let's put that there, Wn sub 2. And of course, we also have, this is 1, and this is Wt2 that's working backwards, because if this is not moving relative to one another, and even if it is moving, they're still in contact with one another. So what I really want to find out is this moving relative to this? And we found out what the criteria is for this to move relative to this, right? So that's going to be theta equals the inverse tangent of mu sub S1. Now let's look at the summation of forces that we have here and what these are. Now we know that W, did we do that? Oh, this was, I've got those backwards. Thank God I've got my little correct type here. That's 1 and that's 2. Sorry. So this would be W sub T1. This is W sub T2. And I think I've got everything else there too. And of course, this is just going to be mu sub S2, I called it, times N of 2 to the surface. All right. We know what WT1 is. WT1 is just going to be the sine. So that's just going to be W1 times the sine of theta. Probably could have put that one closer. And then WT2 is W1 times the, or W2 times the sine of theta. So why don't I just write those? So that's WT1, WT2, Wn1, which equals W1 cosine theta, Wn2, which is W2 cosine theta, and of course these equal, this one here is going to be equal to both of those. So let's get F sub R2 and figure out what that is. So F sub R2, right? F sub R2 is pointing in this direction. These two things are pointing in the other direction. So it seems like mu sub, if I'm just summing the, God, should I have summed those? Should I? Well, N to S. Why don't I solve for that right now? That might be the best. You know, but I could just use mu sub. I don't know if everybody. Yeah, let's do that. So summing the forces in the y direction equal to 0. All right. That's going to give us N to S minus W1 cosine theta minus W2 cosine theta. All right, let's just put a line through there so we know where we are. So we can also see from that summation that we're going to get that N to S is just going to be equal to cosine theta times W1 or plus W2, right? Because I kept that there. I brought these on the other side of the equation, so they became positive, and then I took the cosine out, and that's just W1 plus W2. So let's just put that there like that. And then we know that this times mu sub S2 is going to give us F sub R2. So let's just sum the forces in this direction then. Here, let me get rid of this for a second. Now, if I'm summing the forces in the x direction equal to 0, right? So summing the forces, It's going to be f sub r2 minus wt1 minus wt2. Now, if I'm going to write that out, this is going to be mu sub s. Let's just write it all out here. That equals 0, right? So if we take that equation and we substitute in our identity for f sub r2, right? Because we know f sub r2 is going to equal this plus this. I think everybody can see that. We get mu sub s2 times cosine of theta times w1 plus w2, right? Because isn't that just mu sub s times that? That's just f sub r. And we know that that has to equal the other side, w1 sine theta, w2 sine theta. So we can take sine theta out of there and just have w1 plus w2. All right, I know I'm sort of all over the place here, but we get to cancel some things out. You can see that this times this times this, I really didn't need those brackets, did I? And I've got this times this, so I really can get rid of these on both sides, and that certainly makes my solution to the problem all that much simpler, doesn't it? Because what this says is that the inverse tangent of mu s2 equals theta. Now I can stack these up as high as I want. I'm still going to get that thing. And so it really comes down to, if you look at this result and this result here, it really comes down to the fact that what is the, if we look at these stacked boxes on the inclined plane, it comes down to which one of those surfaces, the surface between 1 and 2, or the surface between 2 and the surface of the inclined plane, has the lower static coefficient of friction. Do you see how that works, everybody? Okay, great. Now, I want to look at another inclined, I didn't even turn that on, did I? No, I have no idea how long this has been going. I wish that they had something up there. I'm sure that they do. They probably have some type of timing aid or something that I just can't see. Now, what I wanted to do is I wanted to look at another example of an inclined plane, just an example problem. I'm just going to cut out some of my board here so that we can have some more room. In fact, that's not the best pen to cut it out with. I actually have the best pen to cut that out with right here that I use to do my blocking, my original blocking. Look at that. Isn't that a great pen? Yeah, that's what putting your Sharpie in acetone does. All right, so the next thing that I want to do is I want to look at an inclined plane problem again. It's going to have a little higher angle of inclination. And we're going to solve this problem, but then what I want to do is I want to look at the problem in a more analytical form. And that might come in the next lecture, because I think I've got one more lecture on friction in the series on friction here. But let's just do this as I have the problem written, and then I want to again, like I say, look at how we could further attack this problem and find out more information than we already have. So this is what I've got here. I've got actually an angle. I'm going to give you the angle. The angle is 36.87 degrees, and you'll immediately recognize that 36.87 degrees is a 3-4-5 triangle, right? A 3-4-5 triangle. The weight that we have for this example problem is going to be 300 pounds. And this force that I've got pushing up here is going to be 100 pounds. You're probably saying, pounds? I can't think in pounds. Sure, you're going to have to think in pounds because that's, that's part of the American engineering profession, believe me. The way that I want to set this up, like usual, is I'm going to set it up so that I've got its free body diagram Cartesian coordinate system set up that way, right? And that's what I want to do, is to look at this as a free body diagram and replace the forces that I've got on there now with the forces that I'm going to have on here. So I'm going to have a 100-pound force. I want to work in pounds because you're going to work in pounds all the time, too. And then I'm going to have a force down here. Why don't we figure out what that force is, right? We know that that force is going to be the cosine of 36.87, right? So 300 pounds times the cosine of 36.87 gives me 240 pounds. So this is going to be 240 pounds. And I'm just going to write in there what that is. It's 300 pounds times the cosine of 36.87, right? Okay. I'll put parentheses around that. And that's 240 pounds. So that's working down. Now we know that we're also going to have another component of the weight force that's working back in that direction, right? And we know that that's going to be 300 pounds times the sine of 36.87 degrees, and that's 180 pounds pushing back, right? So if we've got 100 pounds pushing up and 180 pounds pushing back, then what way, we also have, of course, I'm just going to put that up there. That is my normal force. And my normal force, I think everybody can see, is going to also equal 240 pounds. So when we look at this, we have to take into account now what because the impending motion is to go to the left. I think everybody can see that. So we can see that the frictional force is going to work to the right, right? And that frictional force is going to grow. Now, is there impending motion? Is there going to be motion of this down the inclined plane? Well, that all depends on if F sub r is greater than 80 pounds, isn't it? Can everybody see what I've got here? That the difference here is 80 pounds. Let's figure out what F sub r is going to be. F sub r, well, I have to give you a little information, don't I? Well, mu sub s is going to be 0.25, and mu sub k is 0.2. All right? So we can figure it out. It's going to be 0.25 times the force, 240 pounds. So F sub r max can only be 1/4 of 260, or 60 pounds. Oh my God, that's not going to do it, is it? That's not going to do it. The 60 pounds is not as high as 80 pounds. And the 80 pounds is what's pulling this down here. Even though I've got 100 pounds pushing it back up, the truck is slowly rolling downhill. I guess it wouldn't be a truck, it'd be a sled. The sled filled with medicine for the Eskimos is slowly sliding down the hill. Even though I'm trying to push it up with 100 pounds, it's slowly sliding down the hill. How fast is it accelerating down the hill if all I can do is push it with my 100 pounds between my boots and the frozen ice underneath me, right? Well, it would be 0.2, right? So this is FR max, so this is my static, but what is FR max kinetic? That would be 0.2 times 240 pounds, right? So that's 48 pounds. So if the thing is still rolling down on me, I'm still pushing up with 100 pounds. Once it starts sliding back, right? This is no longer going to be helping me out with 60 pounds so that I only, it's going to be coming down with 20 pounds. No, now it's going to be coming down with the 48 pounds, right? So 80 minus 48. So that's 32 pounds that it's going to be coming down. So when I actually look at the summation of forces in the x direction, it's no longer zero, is it? It's mass times acceleration. Did I forget to give you the, no, I gave you 300 pounds. So the weight is 300 pounds. What's the mass? Isn't force equal to mass times acceleration? And isn't the weight force equal to mass times the gravitational acceleration? Right? So doesn't that mean that mass equals weight divided by the gravitational attraction? Doesn't that mean that the mass of that 300-pound object is equal to 300 pounds divided by 32.17 feet per second squared? Isn't that what that means? You're probably saying 32.17 feet per second squared. Well, how many feet are there in a meter? 3.28 feet equals 1 meter, right? So 9.81 meters per second squared equals, let's just multiply that by 3.28. 3.28 times 9.81 is 32.18 feet per second squared. You see how that works? So that's right. So 300 pounds divided by that, 300 divided by 32.1, actually, it's like 1.7, 6. Anyway, I get 9.32. 9.32 what? Kilograms? No. Slugs. The unit of mass in the British gravitational unit system is slugs. That's right. And we take the pounds. This is a weight, 300 pounds. So we have to turn it into slugs to find out the mass, don't we? That's right. And that's what our mass is right here. But anyway, let's take this a little further. We want to sum up all of the forces, don't we? Now we know that we've got a 100-pound force minus a 180-pound force plus 48 pounds, and that's from our frictional. That's our frictional kinetic. Our kinetic, because the thing is sliding, right? So when we add all of these all up, that still leaves me with 32 pounds, doesn't it? 32 pounds of force. 32 pounds of force has to equal mass times acceleration. So the acceleration of that box, of this box down the slope, right, is going to be 32 pounds divided by 9.32 slugs. 32 pounds divided by 9.32 slugs. And that's right, isn't it? Because pounds divided by slugs should give us feet per second squared. Pounds divided by slugs should give us feet per second squared. Sorry. And I get 3.43 feet per second squared. That's our acceleration of that package. So, yep, I'm trying to push the sled up the hill to get the medicine to the Eskimos in the Diderandi or whatever it is. And with my thing, my dogs just can't pull it up there. They're only giving me 100 pounds of pull, and then I start sliding down. I'm sliding down the hill. And I'm sliding down the hill. And now that I'm starting to go into kinetic friction rather than static friction, I'm sliding faster down the hill, and I'm accelerating down the hill. Actually, I'm accelerating at quite an exceptionally fast acceleration. If you remember the acceleration that we had, that's about 1/3 G, right? So I'm just stopping myself from dying right now by keeping that that dog sled going up and down the hill. All right, I did not put the timer on. I don't know how long this has been for this lecture. I do have another good lecture, following this. That's I think is gonna. I don't know if I'm gonna do another one on. Don't know if I'm going to do another one on inclined planes because we've done quite a few. I think I'm going to just move on into centroids and centers of gravity. And then, that will take us also into moments of inertia and things like that. All right. All right. I will see you in the next lecture.